everyone, and thanks for joining us for the December Causal Inference Interest Group Seminar Series from the Alan Turing Institute. Today, the speaker is the interest group leader, Peter Tennant. So Peter is an associate professor of health data science at the University of Leeds, and he has also been a Turing Fellow for over 5 years now. So his background is in perinatal epidemiology, but his research is now focused on adapting and translating modern causal inference methods into health and social science research. And today, Peter will be talking about how to depict deterministic variables within DAGs, and he'll discuss the benefits of identifying deterministic variables and how to interpret causal effects that might involve derived variables and compositional data. And over to you, Peter.
Thank you very much, Georgia. I should just share my screen. And then, of course, I lose sight of everything. Can you see and hear me still? Okay.
Yes.
Brilliant.
It's working.
Excellent. Thanks for the introduction. It is genuinely a delight to be speaking to the Causal Inference Interest Group, using my prerogative as host to sneak in one of my own presentations. Today it's quite amazing actually to see, I think over 100 people have joined, which is pretty amazing given the title. Depicting deterministic variables within directed acyclic graphs, an aid to identifying and interpreting causal effects involving derived variables and compositional data does not sound like the most urgent topic in causal inference at the moment. Hopefully, I will convince you that there is some value here. If nothing else, there is an interesting little story to tell, which hopefully should entertain. So before I start, I should just declare that I do have a competing interest, which is that I'm director of a small private company in the UK that offers causal inference training and research consultancy services. Therefore, every single time that I publish or speak about causal inference methods, and particularly where I demonstrate the need for or benefits of causal inference methods, I myself may financially benefit. So bear that in mind as you're listening to my arguments in favor of this. Maybe I'm overly enthusiastic about their benefits for reasons not entirely scientific. So this is a long story. The work itself has been kind of in progress for over 5 years, but the theory behind this work is even older. In fact, it goes all the way back over 100 years to Carl Pearson in 1897, who published a short paper on what he described as a form of spurious correlation, which may arise when indices are used. For the kind of statistical historians, as far as I could tell, this is the first use of the term spurious correlation, and it was defined to describe this very specific phenomenon that was taking place that Pearson wanted to highlight, which is, in its original version, if you take two random variables, say x and y, and you divide them by a third random variable, n, so you produce these ratio variables or indices, x over n and y over n, then they will share a spurious correlation. They will share a correlation because both of them contain 1 over n. So that's what he was writing about predominantly, and what he was trying to warn about back in 1897, that if you did this, if you created these indices and then tried to compare two indices that had the same denominator, then they would share a correlation, and that correlation was not necessarily very meaningful. In the following 100+ years, many other authors of incredible esteem have tried to raise concerns or awareness about the same problem. So I think most famously, and certainly most interestingly, Neyman in 1952 essentially wrote a piece about exactly the same phenomenon with a much more interesting example and certainly much more accessible to read for the non-technical expert, where he was asking, do storks bring babies? And showed that if you were to take data on the number of babies in an area, the number of storks in an area, and the number of women of childbearing age, and created two indices, babies divided by women and storks divided by women, then they will share this correlation. Neyman disagreed with Pearson that this was spurious, but certainly deemed it to be not the thing that you were interested in. And so he argued that whilst the correlation is true, the method of study is faulty. So the idea of creating these two indices produces something that is not of any practical interest to you as an applied researcher. So despite those warnings and many others, the truth is we still see analyses of ratio variables by regression and correlation through the applied research literature. I haven't picked out any recent examples, but I could imagine I could look at papers published in the last year in the news and find some examples where people have analysed two ratio variables. But as a slightly more sort of amusing example, there is this paper, which was not intended as a serious piece of work. It was more intended to try and demonstrate the issue of confounding. But nevertheless, it shows the issue quite nicely. It looks at the relationship between chocolate consumption per capita and Nobel laureates per capita, and finds this nice, strong correlation here between the two, which is exactly what, in a sense, Pearson and Neyman and many others would warn is likely to happen when you calculate those kind of indices and you compare them by regression or correlation. So it's a common practice, and it's frustratingly common in applied science. And so really this work originated by a group of us at the University of Leeds asking, can we make it easier for people to understand this problem? Can we make it easier to avoid this problem? And at the time, I in particular was very interested in using causal diagrams to sort of demonstrate statistical phenomenon that were not very widely understood. And so we sort of collectively asked, could we use causal diagrams to help the applied scientific community to better understand issues like Pearson's spurious correlation? And the work really, to begin with, was adopted by Laurie Berry. This was my colleague who at the time was doing her PhD at the University of Leeds. And as part of that, she wondered, how could we incorporate ratio variables within DAGs in a way that highlights the issues and makes people understand what's going on a little bit clearer. And that work took her to this poster that was presented at the European Causal Inference meeting in April 2018. But as we did that work, we also delved more and more into the complexity, as you would imagine, and discovered, ratio variables are not a singular thing. There are many different types of ratio variables. They each have different types of causal structures, and how is best to think about all of this? So we buried ourselves further into the literature to try and find some advice. And this is really where Kellen Arnold also came in. The summer of that same year, the three of us were, I suppose, had a little more time on our hands, and we were reading and really starting to think about how could you think about including these variables more explicitly within DAGs. Now, originally, that actually led to us producing this paper in the International Journal of Epidemiology about 18 months later on compositional data and how could you understand compositional data using DAGs. But it's been a much longer process, I think it's fair to say, to really try and produce something a bit more general that covers more than just compositional data, which is what I'm trying to present today. The reason I'm presenting it largely is because most of that team no longer work at the University of Leeds. They've moved on to other places to do possibly more interesting things. And my passion for this has meant I've been sort of left with trying to drag this ball over the line and see if, you know, we can produce something useful. So before I delve in with the specifics, I'll very briefly just mention about the use of causal diagrams within certainly health and social science research. I don't have time to introduce causal diagrams, so I am assuming that you've all come across, in particular, directed acyclic graphs. So causal directed acyclic graphs, I think it's fair to say, are becoming very popular. They're certainly one of the most popular forms of non-parametric causal diagram, and applied scientists use them to represent the hypothesized causal relationships that are taking place within a system. And so what we do is we represent individual variables with these nodes, and we then draw these arcs or these arrows between them to depict what we believe to be causal relationships. And then those arcs collectively form paths which have various different properties and various different types. And the rule for directed acyclic graphs is that you can't have a cycle. So what a variable at one moment in time can't cause itself at that same moment in time. And so you can't have an instantaneous cycle. So DAGs, as I've just indicated, are increasingly used now in health and social science research. And most of the time they are used for the bread and butter activity of trying to estimate causal effects in observational data. I think it's nearly 3 years ago that this review was published, where myself and many colleagues tried to look at the use of causal DAGs in health research and came across well over 200. But since then, really, they have taken off even more dramatically. And in health, you will find easily, this was basically a 10-minute search of Google Scholar, you will find introductions to causal DAGs in almost every single subdiscipline you can imagine. So we've got primary care education, pediatrics, oral disease, surgical research, cardiovascular disease, trauma, substance abuse, addiction research, anesthesiology, etc., etc. This is not a complete list. Likewise, in many subdomains within social sciences, you'll see there's a ferocious number of introductions as this becomes a standard tool in observational research. But there's another thing that DAGs have proven very useful for, and arguably more useful depending on who you talk to. And that is simply helping to understand, to recognize, understand, and avoid certain methodological issues. So I would argue within the domain of health, for example, the utility of DAGs for helping the wider community to recognize and understand collider bias and selection bias has been by far the most revolutionary aspect of this technology. And there are countless different papers that I could cite, which have become really pivotal references amongst the applied research community. As a slight aside, the methods have also been used to resolve a number of different paradoxes which have confused, or apparent paradoxes, which have confused us as a community for decades, to be honest. It might seem easy once the answer is there, but things like the birth weight paradox and the obesity paradox, at least to a certain extent, can be much better understood with the aid of causal DAGs. So the general aim of this work, as an extension of what I said earlier, is can we use DAGs in a similar way to help applied scientists to recognize, understand, and avoid some methodological issues? And specifically, the methodological issues we hope to help with are those that complicate analyses that involve a deterministic variable. I'm going to explain what I mean by that in a second. So start by saying that DAGs are essentially created and almost always used to depict and consider probabilistic relationships and probabilistic variables. So what I mean there is that when we draw any variable within a DAG, we are usually making a statement that it's caused by some other variables that we've included and something else. And perhaps that something else is quite random. So in this example, we have this variable x, which is caused partly by x1 and x2. But what we're saying is it's not completely caused. You wouldn't know the value of x just from x1 and x2. There is some unknown mechanisms taking place. It might just be pure randomness, which we could depict here by this little ex, as you might do in a non-parametric structural equation model, to say that x is partly determined by x1 and x2 and partly by these other features. Now, in practice, because that's universal within DAGs, because we're almost entirely depicting probabilistic relationships, we don't need to include those error terms. It's automatically obvious that when we draw a variable, there are some other features that are causing that variable that are not part of the DAG. But there are situations in health and social sciences where deterministic variables occur. And indeed, they don't just occur, they are actually quite common in practice. So what do I mean by a deterministic variable? Well, this is an adaptation of Schachter's definition, but we call it a variable that is fully determined by one or more other parent variables, so that the value can be known with certainty once the parents are known. In other words, once we know the value of the parents, unlike in those other situations, we now know the value of that child variable, of that deterministic variable. And in practice, these tend to occur in two different sort of types and settings, which I'm very briefly going to try and introduce. So the first, which I think more people will be familiar with, is the context of a derived variable. So this is a variable that we create, a variable that's been functionally created from one or more other parent variables. And there are two different sort of forms of these. One, a simple derived variable, that's just a variable that has been functionally created from a single parent. The most common form of this is a dichotomized variable. This is where we create, for example, hypertension, a binary variable, 0 or 1, we create by deciding on some thresholds of a parent variable. So here, depending on the level of systolic blood pressure, we have defined hypertension. But it doesn't have to be dichotomous. There's many other types of simple derived variables we could create. Also common are categorical variables. The UK degree classification, in a sense, is a simple derived variable that we take from thresholds of the average grade. So if it's equal or over 70%, then we classify that as a first. If it's in the 10% below that, we classify that as an upper second, and so on. So that's a simple derived variable. Then we also have composite derived variables. And essentially these are the same, but they have two or more parents. For example, GDP per capita. We have taken GDP and we have divided it by population. Body mass index. We have taken weight and we've divided it by height squared to create this derived variable. A change score, which are very, very common in health and social science. We simply take the follow-up measure of a variable and we subtract a previous measure, again, to create this derived variable. And then there's many others and more complex forms we could consider. So in the health sciences, there's a concept known as metabolic syndrome, which is essentially a function of 4 or 5 different parent variables. If you have 3 or more of those parent variables are above a particular threshold, we say you have metabolic syndrome. And if you don't have 3 or more, then we say you don't. So these are very, very common. The other form of, the other occasion where you come across deterministic variables is in a particular type of data known as compositional data. So this is a form of hierarchical data that contains part variables that perfectly sum to a whole variable or a constant. So actually, there's an awful lot of compositional data out there, but it's just less likely that you have necessarily come across this concept. So to give you a couple of examples, your height is determined by the sum of the length of your leg, your trunk, and your head. And likewise, the total daily calorie intake can be considered to be a sum of the intake from the different macronutrients. So the carbohydrate plus the fat calories plus the protein calories. And then equally, we could be looking at something like your total monthly expenditure and say that this, again, is a perfect sum of the amount you spend on rent, bills, food, leisure, and everything else. So that's compositional data. So both of these types of deterministic variables occur very often, but there is a slight problem, which is that standard DAGs, which are probabilistic, are not inherently compatible with deterministic variables. And the reason for that is that those variables carry some additional statistical implications that we otherwise need to deal with. Now, you may not know that from a mathematical point of view, but you may know from a practical point of view that if you've tried to naively include a deterministic variable within a DAG, like here we have body mass index causing diabetes, and we've drawn some confounders, that you can quickly run into some conceptual problems. And in fact, only, I think it was last week on Twitter, I came across a conversation between some applied scientists debating about, well, I'm interested in the effect of BMI. What exactly is the role of height and weight? And the problem is, if you look at this as a probabilistic DAG, it's very unclear exactly what's going on. Are height and weight confounders for the effect of BMI? That's certainly how we've drawn them here. So that would suggest that the effect of BMI can be obtained by adjusting for height and weight. But philosophically, what is the effect of BMI once you have conditioned for both of its parents? Can it have one? So this kind of situation is common, and what tends to happen is people just disregard the complexity and return to thinking about BMI by itself. There is an alternative approach, an algorithmic approach, which is out there, which is to say, okay, deterministic variables ruin our ability to use various causal discovery and identification algorithms, so let's just find any deterministic variables and remove them. So, for example, Schachter's deterministic node reduction algorithm identifies variables that have been fully determined within a network and flags them up as a deterministic node, and then says, okay, let's move any arcs onto the parents. And then what's left is a barren node, essentially a node that has absolutely no children because it contains no additional information. And in theory, if you follow the algorithm to its conclusion, you can just remove the node completely. And you now have a network that you can run all of your usual algorithms on. Problem is, you've removed, potentially, for some people, the exposure or the outcome of interest. So if you run this algorithm, great, you end up with a network that follows all of the rules. But if you are interested in BMI, you've simply removed it. And in practice, that's not very useful. But perhaps more to the point, in practice, people are not really aware that or thinking about the fact that they're using deterministic variables. What tends to happen is that you draw a DAG with BMI in it, and then maybe you come into some problems, but you're not thinking this is a deterministic relationship. And so they often get included in DAGs without any explicit consideration. And all we are essentially encouraging is that using some notation that we propose, if you are dealing with a deterministic variable, try and depict it explicitly in order to avoid those kind of philosophical problems that you run into otherwise. And we propose various different kind of additional notation for doing that. There is some redundancy in here, but the idea essentially is to really thoroughly flag up the fact that you can't treat these variables in the same way as a probabilistic variable. So, first of all, we say the deterministic variables should have double outline nodes. And the reason for that is that in the previous literature in the 80s and 90s, that was what was done, is these nodes were double outlined. So we think that it's fair to continue with that. The next thing we recommend is sort of following in that vein, is that the incoming arcs should also be double outlined. Now, the reason for this is that these arcs behave quite differently to probabilistic arcs. Arguably, in many situations, they are not occurring over time. They are an instantaneous relationship or connection between these two variables. So arguably, they don't even have direction. But at the very least, by making them double-lined, the idea is that you are reminded not to interpret these arcs in the same way that you would a probabilistic arc. The next thing we recommend is that when the variables are kind of occurring together, is that you put them all within a dashed box. And the reason for this is essentially to say quite explicitly, this is all part of the same variable that's happening at the same time. And so it all belongs here within the DAG, even though we've broken it up into further parts. You know, don't try and overinterpret the ordering of this. The fact is, this is happening at this moment. And then finally, we also recommend that the arc that leaves a deterministic node should be dashed. Now, it's debatable whether there even is an arc that leads a deterministic node. Clearly, Schachter's deterministic node notation argues that essentially any such arcs are irrelevant because they are covered by the arcs coming from the parent nodes. In other words, there is no residual causal effect of a fully determined variable above and beyond what's covered by its parents. However, in practice, many people are interested in the summary effect or the indicative effect, or whatever you might call it, of a deterministic variable. So simply leaving out the arc is not likely to be very useful for many people in practice, but perhaps leaving it there dashed reminds people that this arc is in a kind of philosophical middle space. Whilst you can estimate it, strictly speaking, it represents other mechanisms that are taking place that you have chosen to simplify or average. So let's see what that notation actually looks like in practice. So here we have a simple derived variable, hypertension, and its relationship with CVD. We might draw it just like this. So they are essentially the same variables. So they're enclosed within this dotted box. And we have systolic blood pressure completely causing hypertension, hence the double-lined arrow and the double-lined box. We have a dashed line to say that there is some causal effect that we could imagine coming from hypertension, but we also have a residual line here that represents all of the part of systolic blood pressure that is not acting through the downstream dichotomized variable. So the residual part that would not be picked up if we looked at hypertension alone. So that's what that might look like. Then there's compositional data. So suppose we're interested broadly in the relationship between energy intake and diabetes. Well, we might draw it like this, where we have the three components: carbohydrate intake, fat intake, and protein intake, all causing total energy intake. They are all happening at the same time, so they're all within this dashed box. We can imagine the effect of increasing total energy on diabetes with this dashed arc here, but then we could also imagine a residual effect above and beyond merely increasing calories for carbohydrates, fat, and protein that are represented here by the colored arcs. So you see how we're sort of still trying to reflect different ways of thinking about how the causal effect could break down. And then finally, we have a composite derived variable. So let's imagine if we're interested in the effect of BMI on cancer. That might look something like this. We no longer have a dashed box because height and weight do not necessarily occur together. If this was an adult sample, then your height occurred up to around early adulthood, but your weight continues to occur thereafter. So now BMI itself has a complex temporal footprint, but again, we can imagine that the summary variable BMI has some effect on cancer, and there's some other effect not reflected by BMI caused by height and weight shown by the individual arcs. So that's what we do. But you might be sat there thinking, I don't understand what on earth the benefit of this actually is. And I'm going to spend the rest of the time trying to convince you of at least one or two benefits. So the first, well, here are the main ones in summary. First, we think it helps to identify and avoid misinterpreting something called a tautological association, which I'll introduce in a moment. Secondly, I certainly think it makes it easier to plan and interpret analysis of compositional data. And then finally, when working with derived variables, I think it can really help you to more formally consider the assumptions that you're relying on. So is this the target estimand that I'm actually interested in? And can this variable satisfy assumptions such as consistency and exchangeability? So first, I mentioned tautological associations. Well, what are those? Well, these are the self-fulfilling associations that arise when a deterministic variable is analyzed in direct relation to one of its parents or a sibling variable that shares another parent, a parent component. So as a very low-level example, it should be obvious that a derived variable, simple derived variable, will share an association with one of its parents. I mean, it's been defined as such. So we imagine systolic blood pressure and hypertension. It looks something like this. When you've depicted it like this, it tells you hypertension is defined by systolic blood pressure. So going out and calculating the correlation between them would be surely absolutely a waste of time, because although blood pressure causes hypertension, it only does so because we have defined it as such. That has no real practical utility. But perhaps by defining the relationship in this explicit way, it will prevent people from accidentally calculating these correlations and trying to interpret them more usefully. Now, you might think, I don't understand why that's ever needed. It should be absolutely obvious that a derived variable will be correlated with its parent variable. But there are examples in the literature of tautological relationships being considered, particularly at summary level. So this is where maybe you've got means and so on within groups or within countries. So here are just two examples from this paper where they've plotted the relationship between mean systolic blood pressure and the prevalence of hypertension on the left there. It's not quite a perfect correlation because in practice, hypertension is also defined by diastolic blood pressure. But on the right here, mean alcohol consumption and prevalence of heavy drinking, when heavy drinking is defined by alcohol consumption, this is an almost perfect relationship. And the only difference there is essentially driven by distributional differences. Not a very useful piece of information. Perhaps this kind of correlation would be avoided if we more explicitly flagged up our variables using DAGs beforehand. Now, in practice, misinterpreting simple derived variables is probably very rare, but misinterpreting composite derived variables is more common. And one of the most common that occurs here is ratio variable. So this was the example that Pearson and Neyman were trying to warn about, that, for example, you might have a situation like this, where the GDP is caused by population size and the CO2 emissions are caused by population size. The attempted solution to this is to divide both by population size to produce these indices or these ratio variables. But in doing so, you do not remove the relationship caused by n, you simply alter it. You will still expect there to be a tautological association between these two sibling variables because they both share 1 over n in their parentage. So in reality, if we wanted to deal with n, if we wanted to deal with that unwanted correlation there, well, if we just draw a DAG and look at it, it should be obvious that n is actually a confounder for the relationship between GDP and CO2 emissions. So we would just condition on n. We would not divide by n. That would be the appropriate way of asking what is the relationship between GDP and CO2 emission independent of population size. Moving on to compositional data, deterministic variable notation can really help here and help with understanding and planning your analyses. So let's give a common example. Nutritional epidemiology is a domain that is interested in understanding how individual components of the diet may influence health. And because people who eat more of one component, say saturated fat, typically eat more overall, what is common in that domain is to condition on total energy intake in order to sort of control for that and ask what is the effect of saturated fat independent of eating more overall. But is that actually a reasonable approach to get at the causal effect of the individual parts? Well, if you draw the DAG using the deterministic variable notation, then it becomes more obvious what actually happens when you do this. So say we're interested in the effect of the individual parts on the outcome. We would not estimate that by conditioning on total energy, because here total energy is a collider. And so by conditioning on that collider, what do? We introduce a dependency between all of the components that cause total energy intake. So in fact, when we condition on total energy intake, we no longer get the total causal effect of, say, carbohydrates. We get, because any increase in carbohydrates for the same total energy intake must be accompanied by a decrease, in this case, in both fat and protein intake. So what we end up doing when we condition on this collider here is we turn our effect into a substitutive effect. So we would estimate in this example the relative compositional effect of carbohydrates instead of fat and protein. What happens if we additionally adjusted for fats? Well, that would remove fat from that substitution. So now both the total energy intake and fat would be fixed. And what we would estimate, again, would not be the total causal effect of carbohydrate. It would be the effect of carbohydrate instead of the only thing that's allowed to freely vary, which here is protein. So if we didn't want to estimate a substitution, if we wanted to estimate the total additive effect of carbohydrates, then, as I say, we don't want to be conditioning on total energy intake. The DAG helps you to see that. What we want is the sum of the effect of increasing total energy intake through increasing carbohydrates and the unique part of increasing carbohydrates. So actually, to do this, the best way would be to condition on all of the other components of total. That would not only reduce variation in the outcome and give us a much cleaner estimate of the part that's due to carbohydrates, but it will have the additional benefit of blocking any confounding via common causes of the diet that are acting through the diet. So that's compositional data. So finally, how can deterministic variable notation help us with identifying the causal effect of derived variables? Well, I think there's three ways. First, it forces you to ask the important question, is this really the estimand that we're interested in? And then if it is, it forces you to consider, or it encourages you to consider, what are the implications for consistency and exchangeability? So the first thing it asks is, are you sure this is the thing you want to estimate? So many composite-derived variables are made in order to standardize the effect of one component while controlling in some way for another. So BMI is the classic example where what we're trying to do apparently is create a measure of weight that in some way accounts for differences in height. But in fact, as with the other ratio variables, BMI retains information about height. It's simply changed it. Okay, it has to retain it because it's made from height. So what you really get when you estimate the effect of BMI is the joint effect of weight and 1 over height squared. And so the question you need to ask yourself if you're using BMI is that really the estimand that I'm interested in? I would wager for many people that it's not. That in fact, you're interested in the effect of weight independent of height. Well, if we look at this more simple DAG with BMI removed, we realize height is simply a confounder for the effect of weight on cancer here, and therefore the appropriate way would not be to divide and square, but just to condition. So at the very least, by drawing that DAG explicitly, you force yourself to ask that question, do I really want this joint effect, or is it perhaps something else that I'm actually interested in? Moving on to consistency, I'll only mention this briefly because it's a lot more philosophical and just something to think about. But in strict terms, a composite-derived variable violates the consistency assumption. And the reason for this is because the same value can be obtained from essentially an infinite number of combinations of the parents. So if we had a BMI of 30, well, that could mean that you have a weight of 98 centimeters and a height of 1.83 meters, or it could mean you have a weight of 78 centimeters and a height of 1.61. Very, very different underlying parent variable combinations, but the same BMI. So the idea that a single unit change has a fixed definition is clearly extremely dubious. And I would argue that in fact, when you're working with composite variables, the estimated effect of that variable is likely to transport extremely poorly because it relies on the assumption that the parent variables in every population that you're transporting to have exactly the same contribution to that deterministic variable. The other thing that's important to bear in mind from a consistency point of view is that there are particular problems with composite-derived variables when it comes to instrumental variable analyses. So, suppose you are interested in estimating the effect of obesity on cancer using an instrumental variable approach. So you have chosen some genetic instrument for obesity. Obesity here is a downstream child of BMI, which itself is a child of height and weight. The problem is that the exclusion restriction assumption requires that the effect of our instrument acts entirely through our exposure, here obesity. Well, when we think about what obesity actually means, height and weight, what we're saying, and the fact is obesity is only a downstream consequence of height and weight. In reality, our instrument will not be causing obesity directly, but it will be influencing height and weight. What we are saying in order to estimate the effect robustly is that our instrument must not have any residual path via height and weight. So height and weight cannot cause the outcome independent of the downstream constructs. To me, that seems very, very unlikely. It means there would be, in the case of obesity, absolutely no dose-response relationship for either height or weight. So in practice, I would argue that most instrumental variable analyses, the underlying exclusion restriction assumption is violated in the context of derived variables, particularly composite derived variables. So finally, the final thing that you need to ask, and you need to be asking this anyway, is can I actually identify my causal effects of interest when I'm interested in a composite derived variable? So to do that, usually we need to check the role of all of the contextual variables, identify the confounders and condition on the confounders. But when we're looking at a composite derived variable, this means we've added an assumption. And that assumption is that all of the contextual variables have to have essentially the same relationship with all of the components. So suppose we're considering the causal effect of metabolic syndrome on CBD. We might draw it naively like this. But what we know is that in reality, metabolic syndrome is made up from 4 parent variables. Again, it's slightly naive to draw them like this, because in reality, they're not all occurring at the same time. For metabolic syndrome, it's probably more like this, where the waist circumference is determining lipid concentration and blood pressure, and together they're all in turn determining glucose concentration. So in order to be able to have an identifiable causal effect, for metabolic syndrome, all of the confounders must act before all of these 4 variables. So that means they must look a little bit like this. Maternal weight, your mother's weight when you were born, caused all of these things as measured now. That's a nice, simple confounder. We can adjust for that cleanly. What we mustn't have is a situation that looks like this, where there's a variable that confounds some of the variables within metabolic syndrome, but is actually a mediator for some of the others. Many of you will know this situation as time-varying confounding or intermediate confounding. If we were dealing with each of these terms individually, there are ways to do that. But if you've thrown it all in your model under the single node of metabolic syndrome, essentially no causal effect can be identified once you have intermediate confounding. So the benefits of thinking explicitly about your derived variable is to force you to ask, are we absolutely sure there are no variables that sit within the definition of this variable? So the causal effects of composite derived variables are likely to be particularly difficult to identify when the composite derived variable has many parents, as we just saw, and particularly when those parent components don't arrive simultaneously in time. So those composite variables that add together or otherwise combine information from multiple different time points are likely to be particularly difficult to identify a causal effect of. And this, I think, has potentially major implications for health and social science research, given that derived composite variables are so common in that domain. So, to summarize, derived composite deterministic variables are ubiquitous, essentially, in health and social science research due to the occurrence of both derived variables and compositional data. Unfortunately, there are a number of analytical and interpretational challenges that these variables bring, and that those challenges remain not very well understood, which leads to some common errors that pollutes the literature. We believe that with explicit notation, DAGs might provide a useful aid for planning and interpreting the analysis and therefore avoiding these problems. And so we're encouraging researchers to consider using this notation when they're working with derived variables and or compositional data. I have some references here, which I guess if you're watching the YouTube later, it's easier to pause and look at. Otherwise, they will be available later on the YouTube channel for you to look at. Also, in the fullness of time, the paper behind all of this work is now in press in the American Journal of Epidemiology. But if you want to read an earlier version, noting that some of the ideas have changed thanks to some really fantastic peer review, there's some earlier version of these thoughts are also available in preprint form.